In this video, we are going to answer a very practical question in the finite element method. How do we choose appropriate shape function terms? To answer this, I will introduce one of the most fundamental consistency checks in finite element method, the patch test. We'll see how the patch test helps us verify whether a chosen interpolation can exactly represent basic displacement and stress fields, and why passing this test is essential for any reliable finite element formulation. In this video, we will focus on two-dimensional finite elements and use simple 2D examples to explain the key concepts clearly. Let's first remind ourselves why shape functions matter in finite element analysis. In FEA, we approximate the displacement field inside an element rather than knowing it exactly. For a two-dimensional element, the displacement components are uxy and vxy, and they are expressed using shape or interpolation functions. At any point inside the element, the displacement is written as a weighted sum of the nodal displacements, where the weights are the shape functions, as you can see here. So Ni represents the shape functions, and we use the same Ni for both u and v interpolation. This means that everything the element can represent, its accuracy, its deformation behavior, and its numerical performance comes directly from the choice of these shape functions or Ni's. So in particular, the choice of Ni or shape function controls the accuracy of the element, its ability to represent the rigid body motion and constant strains, and its numerical stability, including the avoidance of locking or spurious modes. To choose appropriate shape functions, we need to understand the basic requirements for displacement interpolation. Any valid set of shape functions must satisfy three key requirements. First, rigid body motion. The element must be able to reproduce pure translations and rigid rotations without producing any strain. This is essential because rigid body motion should not generate internal forces. If an element fails this requirement, the stiffness matrix will produce spurious stresses. Second, constant strain rate. The element must be able to reproduce a state of constant strain, and constant strain actually corresponds to linear displacement field. This ensures that uniform stress fields are represented correctly, which is a minimum requirement for accuracy in solid mechanics problems. The third requirement is completeness. The polynomial basis used in the displacement interpolation must be rich enough to represent the chosen order of approximation. This is where tools like Pascal triangle become useful, as they help us systematically construct complete polynomial bases. These three requirements form the theoretical foundation behind the patch test, which we will introduce next. Now let's introduce the key idea of this video, the patch test. The patch test is a simple but very powerful way to check whether a finite element formulation is good enough to produce correct basic results. At its core, the patch test asks a very simple question. Can the element reproduce simple displacement and stress fields exactly? If the answer is yes, then the element will generally give reliable results when it is used in more complex problems. So why do we need this test? In finite element analysis, displacements inside an element are approximated using interpolation or shape functions. If those shape functions are poorly chosen, the element may introduce spurious stresses, even under very simple loading conditions. The patch test acts as a quick diagnostic tool. It tells us whether the interpolation space is sufficiently complete to ensure correct physical behavior. Let's now look at what is actually tested in the patch test. There are two main versions of the patch test. The first one is the rigid body motion test. So in this test we apply pure translations or a rigid rotation to a small patch of connected elements. In this case, the correct strain and stress state is 0 everywhere. If the element produces 0 strain and 0 stress under rigid body motion, then it passes this part of the patch test. Second, the constant strain test. Here we apply nodal displacements that correspond to a uniform strain field. For example, a linear variation of displacement in the x or y direction. The correct result in this case is a constant stress field throughout the patch. If the element reproduces this exactly, then it also passes this test. If an element fails the patch test, it will very likely give incorrect results in general meshes, such as locking, spurious stresses, or unstable stiffness behavior. On the other hand, if the element passes the patch test, it is considered convergent, meaning that as we refine the mesh, the numerical solution will approach the exact solution. Let's now look at a concrete example of the patch test using two-dimensional element. Here we consider the T3 element, which is the three-node linear triangular element. The shape functions of the T3 element are linear functions of x and y, as shown here. Each shape function is of the form a constant term plus a term linear in x and y. So we have a constant term and linear forms of x and y in all of the shape functions. Because of this, if you, for example, want to interpolate u or v using the shape functions, ui are the nodal displacements. The T3 element can exactly represent, it comes here, any linear displacement field such as uxy equals to a plus bx plus cy. Now let's check the patch test requirements. First, for rigid body motion, the displacement field is constant or corresponds to a rigid rotation because of this constant term. Since constants are included in the interpolation, the T3 element reproduces rigid body motion exactly, so it passes this test. Second, for a constant strain state, the displacement varies linearly with position, so we have bx and cy terms, which are linear terms with respect to x and y. Because the shape functions are linear, the resulting strain and stress are constant throughout the element. So this test is also passed. So both of them are passed. As a result, the three-node linear triangle passes the patch test and is a convergent finite element. Let's now look at another important patch test example, the Q4 element, which is the four-node bilinear quadrilateral element. The shape functions of the Q4 element are written in the natural coordinate systems R and S as shown here. As you can see, each shape function is bilinear involving products of terms like 1 plus minus R times 1 plus minus S. If we expand these expressions, we find that the interpolation contains the terms 1, R, S, and Rs. These terms are sufficient to represent rigid body motion through the constant terms and linear displacement variations in the physical coordinates x and y after mapping. Now let's check the patch test requirements. For rigid body motion, the constant terms ensure that zero strain is produced. So because of this constant term, we can have zero strain for the rigid body motion. So the Q4 element passes this test. For a constant strain state, the element must reproduce linear displacement fields. Because the bilinear interpolation includes the terms R and S, The resulting strain is constant, so this test is also passed. Therefore, the 4-node bilinear quadrilateral passes the patch test and is a convergent finite element. To understand completeness more systematically, we use Pascal's triangle. In 2 dimensions, polynomial terms can be organized by order using Pascal's triangle, as shown here. Each row of the triangle represents the complete set of polynomial terms needed to describe a displacement field of a given order. For example, the first row corresponds to constant term, as you can see here. The next row add linear terms of x and y. And higher rows include quadratic, like x squared, xy, and y squared, cubic, like x cubed, x squared y, xy squared, and y cubed, and higher order terms. When we say that an element is complete, we mean that its shape functions are capable of exactly reproducing all polynomial terms up to a certain order. This is critical because completeness guarantees that an element can represent the displacement fields required to pass the rigid body motion and constant strain patch tests. In practice, Pascal's triangle provides a simple and systematic way to check whether the interpolation space of an element is rich enough for the intended order of approximation. Let's now apply the idea of completeness specifically for triangular elements. We start with the 3-node linear triangle or T3 element. This element uses the polynomial terms 1, x, and y, which form a complete linear basis. As a result, T3 element can exactly represent rigid body motion and constant strain and therefore passes the patch test. Next, we have the 6-node quadratic triangle or T6 element. In addition to the linear terms, this element includes quadratic terms such as x squared, xy, and y squared. This makes the interpolation complete up to the second order, allowing the element to capture curvature in the displacement field. So as we move from T3 to T6, we increase the order of completeness, which improves accuracy for more complex deformation patterns. This illustrates a key idea. The order of the shape functions directly determines what displacement fields an element can reproduce exactly. We can continue this progression to higher order triangular elements. Here we have the 10-node cubic triangle or T10 element. This element includes cubic polynomial terms in addition to the lower order ones. So we have x cubed, x squared y, xy squared, and y cubed. As a result, the interpolation is complete up to the third order, meaning that all cubic displacement polynomials can be represented exactly. Because of this completeness, the T10 element naturally satisfies the rigid body motion and constant strain requirements and therefore passes the patch test. More importantly, higher order completeness allows the element to capture more complex deformation patterns with higher accuracy, especially in problems involving curvature or stress gradients. So again, the key takeaway is clear. As we increase the polynomial order of the shape functions, we increase completeness and improve the approximation capability of that element. This figure helps us clearly see the relationship between triangle elements, polynomial order, and completeness. At the top, we have the 3-node triangle or T3 element. This element, the shape functions, include 1, x, and y. This means the interpolation is complete at first order, which is why the T3 element can reproduce rigid body motion and constant strain and passes the patch test. Moving to the 6-node triangle or T6 element, we add the quadratic terms such as x squared, xy, and y squared. This makes the interpolation complete up to the second order, allowing the element to capture curvature in the displacement field with higher accuracy. Finally, The 10-node triangle or T10 element includes cubic terms. This results in third-order completeness. By cubic terms, I mean x cubed, x squared y, xy squared, and y cubed. So this results in third-order completeness, enabling the representation of even more complex displacement variations. So what this diagram really shows is a simple but powerful idea. As we increase the number of nodes, we increase the polynomial order of the shape functions and therefore the completeness of the element. This is exactly why higher order elements perform better in problems with strong gradients or curved deformation patterns. Let's now look at quadrilateral elements and how completeness and the patch test apply to them. We start with the 4-node bilinear quadrilateral or Q4 element. This element uses the polynomial terms 1, x, y, and xy. Although this is an incomplete quadratic set, it is still sufficient to represent rigid body motion and constant strain. So the Q4 element passes the patch test. For this reason, Q4 is classified as a serendipity element. Next, we have the 9-node quadratic quadrilateral or Q9. This element uses the full quadratic polynomial set, as you can see here, making the interpolation complete at the second order. Because of this, the Q9 element is referred to as a Lagrangian element, and it provides higher accuracy for problems involving curvature. Finally, the 8-node quadratic quadrilateral or Q8 element drops the center node. As you can see here, it is dropped in QA and therefore omits the x squared y squared term. This makes the interpolation incomplete quadratic, but it still satisfies the patch test requirements and is also classified as a serendipity element. I will briefly explain the difference between serendipity and Lagrangian elements at the end of the video. This slide simply shows quadrilateral elements mapped onto Pascal triangle. The Q4 element occupies the lowest level and includes only the terms needed for rigid body motion and linear fills. The Q8 element extends the interpolation but still misses the center term, so it remains incomplete quadratic. The Q9 element includes the full quadratic set corresponding to complete second order interpolation. So this diagram visually summarizes where each quadrilateral element sits in terms of polynomial completeness. At the end of this video, I just want to briefly explain about the serendipity and Lagrangian elements. Serendipity elements place nodes only on the element boundaries with no internal nodes. This reduces the number of degrees of freedom, which makes them computationally efficient. They can exactly represent complete linear fields and most, but not all, higher order polynomial terms. That is why serendipity quadrilateral elements such as Q4 and Q8 still pass the patch test even though they are not fully complete. It is also important to note that triangular elements always follow Pascal's triangle exactly, so there is no serendipity version of triangular elements. Lagrangian elements, also known as tensor-product elements, include nodes on the boundaries and inside of the element, as you can see here for Q9 element. The presence of the internal nodes allows them to represent a complete polynomial basis of a given order. For example, the Q9 element includes all quadratic terms and is therefore fully complete at the second order. This generally makes Lagrangian elements more accurate and less sensitive to element distortion, but at the cost of more degrees of freedom and higher computational expense. So in practice, choosing between serendipity and Lagrangian elements is a trade-off between efficiency and completeness.